So in this video, I'm going to go through and explain the multiple choice and free response questions for the Princeton Review Big Idea number 2. Okay. So for number 1, it says, why does calcium fluoride have a higher melting point than NH3? So you need to compare these two molecules. Well, calcium fluoride is an ionic compound, so it has that Coulombic attraction, the lattice structure, okay, between the positively charged calcium and the negatively charged fluoride ions. And NH3 has hydrogen bonding. So the answer is that CaF2 is going to be an ionic substance, and therefore it requires a lot of energy in order to break the ionic lattice, that attraction between positive and negative forces. They tried to trick you with C. If you were comparing two different ionic compounds, then remember you compare charge first and then the size of the ions. But in this case, because one is ionic and one has covalent bonding, we're not comparing size at all, and we're just comparing the fact that one is ionic and one has covalent bonding and hydrogen bonding for the intermolecular force. For number 2, it says, which of the following pairs of elements is most likely to create an interstitial alloy? So there are two different types of alloys. This is something we did not go over, but it's really quick and easy to learn. The two different types of alloys are interstitial and substitutional. Now, substitutional is exactly how it sounds. You've got metals that have very similar size. In interstitial, you're going to have one large type of metal and then another one that's very small. Okay? So if it's asking for interstitial, you're looking for two metals that have very different sizes. If you're looking for substitutional, you're looking for atoms, metal atoms that have very similar size. So in this case, remember, when you move down the periodic table, because you're adding principal energy levels, the farther down you go, the larger the atom becomes. And therefore, because when we're comparing all of these different metals, some of them are just separated by a horizontal difference. That doesn't matter as much, because when you're moving horizontally across the periodic table, you're simply adding protons. That has less of an effect on the size as moving down the periodic table when you are adding principal energy levels. So you want the two metals that have the greatest vertical distance from each other. That will be the greatest difference in size. And so your answer is going to be B, because aluminum and lead have the greatest vertical distance between each other. In 3, it says, why can a molecule with the structure of NBr5 not exist? Well, NBr5, if you had NBr5, that would be an expanded octet. And remember, in order to have an expanded octet, your atom, the atom that has the expanded octet, which in this case would be nitrogen, needs to have access to the d orbital. Well, since nitrogen is in your second energy level, it doesn't have access to the d sublevel. Therefore, the answer is A. Since it only has 2 energy levels, it can't actually expand. For number 4, for 4 through 7, it says an evacuated rigid container is filled with exactly 2 grams of hydrogen and 10 grams of neon. The temperature of the gases is held at 0 degrees Celsius, and the pressure inside the container is a constant 1 atmosphere. What is the mole fraction of neon in the container? So remember, mole fraction will be the moles of neon divided by the total number of moles. Well, I've got to figure that out. So I'm going to take 2 grams of hydrogen, divide by its molar mass to figure out its number of moles. So 2 divided by 2, because remember hydrogen is H2. That'll give me 1. And then for neon, it's going to be 10 divided by the molar mass of neon, which is 20. So that would be 0.5. So I'm going to take 0.5 and divide it by the total number of moles, which would be 1 plus 0.5, which is 1.5. And so the mole fraction, when you do that division, it would be 5 divided by 15, which gives us 1/3. And so that's about 0.33. Then it says, what is the volume of the container? Now, keep in mind, if you are not at standard temperature and pressure, you need to use PV equals nRT, because your pressure and your temperature are not at STP. But in this case, remember, STP is 1 atmosphere and 0 degrees Celsius. So I actually am at STP, even though they didn't say that. So this is a really easy problem, because at STP, 1 mole of a gas has a volume of 22.4 liters. Now, For this problem, my total number of moles of gas is 1.5 moles. I added them up, right? Because you had 0.5, you had 1 from hydrogen and 0.5 from neon. So in this case, I just need to take 1.5, multiply by 22.4 liters per mole, and I end up getting 33.5. Now, if I weren't at STP, you could not use 22.4, and you would have to use PV equals nRT. You can still use PV equals nRT for this problem, and it'll work perfectly fine. But just just thinking about time, using 22.4 when you recognize it is a great idea. For number 6, it says a sample of liquid NH3 is brought to boiling point. Which of the following occurs during the boiling process? Remember, whenever you are changing states of matter, going from a solid to a liquid or a liquid to a gas, you are breaking the intermolecular attractions. Okay, you're not actually breaking the covalent bonds, you're just breaking the attraction between different NH3 molecules. And so, as a result, since NH3 has hydrogen bonding, your answer is going to be D. You're breaking those hydrogen bonds, those intermolecular forces, not intramolecular forces. In 7, it says which gas particles have a higher RMS velocity. RMS simply means just the average velocity, okay? So in order to answer this question, you need to remember that the kinetic energy of your gas, right, the energy of movement, your KE, equals 1/2 mv squared. Now, kinetic energy, the only thing that affects your kinetic energy is temperature. So since all of these gases are at the same temperature, they all have the same kinetic energy. So if you look at the formula now, they all have the same KE. The larger the masses, the smaller the velocity is going to be, which makes sense. Think about a car. If they have the same amount of energy, a huge truck versus a little tiny car, the little tiny car, if it has the same amount of energy, is going to be moving quite a bit faster. So when you look at this, we're looking for the gas particle that has the lowest molar mass, or has the least amount of mass. Not necessarily size, because 1/2 mv squared is not talking about the size, it's talking about the mass specifically. So your answer is going to be A, because hydrogen has a lower molar mass. For 8, it says which of the following compounds would have the highest lattice energy. So now, because all of these compounds are ionic compounds, I can look at charge, and then I can look at size. Okay? So remember, the greater the charge of your ions, the stronger the lattice energy is. Then, if you're looking at ions that all have the same charge, then you can look at the size. And the smaller the size is, the smaller the size of the ion, then the stronger the lattice energy is going to be. So I can automatically eliminate A, LIF. I can get rid of D because that is actually not ionic bonding at all. It is it's a covalent bond, number 1, so it's a molecule, and not only that, it's nonpolar, which means it would just have dispersion forces. So that'd be really weak. Then I need to simply compare MgCl2 and CaBr2. Now, if I'm comparing these guys, if you look at your periodic table, Mg is smaller than Ca, okay, and Cl is smaller than Br, which tells me that MgCl2b is going to have the highest lattice energy. Okay, now I know someone's going to ask the question, well, what if one of the cations is smaller, but then its anion is bigger? In that case, it's anybody's bet. But hopefully in a question that they would give you, both ions would be smaller to make it easy enough to determine which has the highest lattice energy. Okay. For 9, it says the following diagrams show the Lewis structures of 4 different molecules. Which molecule would travel the farthest in a paper chromatography experiment using a polar solvent? So remember, in paper chromatography, the solvent, it is going to pick up and hold on to whichever molecule is the most polar. You want the most polar molecule that will travel the furthest because it's the most strongly attracted to that polar solvent. So if you look at all of these different options, you're looking for whichever one's the most polar. Okay? So when I'm looking at this, methanol is polar. Yes, absolutely. It has 1 hydrogen bond. Pentane is nonpolar, so I'm going to get rid of that one. Acetone is polar, but notice because it doesn't have a hydrogen coming off of that oxygen, it does not have hydrogen bonding. So as a result, it has dipole-dipole attractions, but not hydrogen bonding. And then that ether there, that is perfectly symmetrical, so that is going to be nonpolar. Therefore, since methanol is the one with the hydrogen bonding, which is the most polar as far as intermolecular attractions are concerned, your answer is going to be A. In 10, it says the 6 carbon atoms in a benzene molecule are shown in different resonance forms as 3 single bonds and 3 double bonds. Remember, when we're talking about resonance, it's not that you have 3 individual single bonds and 3 individual double bonds. Instead, what you have is an average of all 6 of those bonds. Okay? If the length of a single carbon bond is 154 and the length of a double is 133 picometers, what length would be expected for the carbon-carbon bonds in benzene? So I actually in my head say, okay, I've got 3 single bonds, okay, plus 3 double bonds, so that's a total of 9 bonds there, divided by 6, so it's going to be about 1.33 if I'm doing my math correctly, okay? So it's going to be somewhere in between the length of a single bond and a double bond. So if I look at all of these answers, I've got to be somewhere between a single and a double bond, which would give me the answer of C, 140 picometers. In 11, for 11 through 14, it tells you have 4 moles of SO2, 6 moles of O2, okay, and they're allowed to react. Okay? Which particulate drawing best represents the contents of the flask after the reaction goes to completion? So this is going to be an ice chart problem. Now, I'm not saying we're in equilibrium. We can use an ice chart by saying initial change and then the end. Okay? There's another problem in this multiple choice just like this. So once I finish this problem, I want you to go and find that one and try it if you had issues with this. So I'm going to create an ice chart. I start off with 4 moles of SO2, 6 moles of O2, and no SO3. My change is going to be negative 2x, negative x, and plus 2x. And so I've got to figure out which of these guys is going to run out first. So if, for example, I said O2, let's see if O2 runs out first. How much change would have to happen in order to run out of O2? Well, I'd have to change by 6 moles. If x were 6, if you plugged that in for SO2, you'd have 4 minus 12, you'd have a negative number, so that doesn't work. So it turns out SO2 is actually going to be your limiting reactant. X, if SO2 were to totally run out, 4 minus 2x equals 0, your x is going to be 2. So x becomes 2 moles, so SO2 is going to be 0. If x is 2, that means 6 minus 2 for O2 would be 4, and then 0 plus 2x would be 4 as well. Okay? So I went from having 10 moles to having 8 moles of gas at the very end. So which of these particulate diagrams demonstrates that? Well, C does, because you've got 4 of oxygen and 4 of SO3. Keep in mind that 10 to 8 comment, because that's about to come into play. Okay? It says if the temperature remains constant, what percentage of the original pressure will the final pressure in the container be equal to? Well, I started off with 10 moles, so that's 100% pressure, and I went down to 8. So that's 80% of the original number of moles is now present. Using PV equals nRT, assuming everything stays constant except for pressure and moles, therefore my pressure goes from being 100% of what it used to be to being only 80% of what it used to be. So my answer is going to be B. At a given point in the reaction, all 3 gases are present at the same temperature. Which gas molecules will have the highest velocity and why? So if they're at the same temperature, you know that your kinetic energy of all of them are going to be the same, which means the one with the smallest mass, that will be the one with the fastest velocity, okay? Because Ke equals 1/2 mv squared. So I know that it's going to be A because O2 has a smaller mass than SO3 and SO2. For 14, it says, under which of the following conditions would the gases in the container most deviate from ideal conditions and why? So remember, to have a gas acting ideally, we want as high of temperatures as possible and as low of pressures as possible, okay? So I know that I can get rid of A and I know I can get rid of D because those are ideal situations, not me deviating from those situations. For B, I agree high pressure could lead to a gas deviating from ideal conditions, but not because they're colliding together, because if you increase pressure, that means you're going to have a greater chance of them being attracted to each other, which means they would not be acting ideally. So that answer's out. So the only answer that makes sense is that at low temperatures, because the gases are moving so slowly, they're more likely to attract each other. So your answer is C. For 15, it says a mixture of helium and neon gases has a total pressure of 1.2 atmospheres. If the mixture contains twice as many moles of helium as neon, what is the partial pressure due to neon? So this is just some basic algebra, guys. If my number of moles of neon is X, that means my number of moles of helium would be 2X. So it would be 2X plus X equals 1.2. That's my total pressure based on Dalton's law of partial pressures. So then I can solve this, and X is going to be 0.4. Okay, which is my partial pressure of neon. And I'm done. It's as easy as that. It's not necessarily that conceptually they're really hard. It's that you need to take the concept and just apply a little bit of math to it. Okay? For 16, it says nitrogen gas is collected over water. If the vapor pressure of water at 25 degrees Celsius is 23 millimeters of mercury and the total pressure is 781, what is the partial pressure of nitrogen? Awesome and easy question. You just know that the total pressure is 781. You know that the partial pressure of water is 23, and that the partial pressure of water plus the partial pressure of nitrogen gas equals your total pressure. So all you have to do is subtract. It's exactly what we did in the lab. So your answer is D. For 17, it tells you that you have 22 grams of a sample of unknown gas, and it occupies a volume of 11.2 liters at standard temperature and pressure. Note that, because otherwise you might be thinking, I can't use PV equals nRT, I don't have enough information. Good news. Since I'm at standard temperature and pressure, I can say 11.2 liters, multiply that by 1 mole over 22.4 liters, and that gives me 0.5 moles because I'm at STP. To figure out the molar mass, I would just take 22 divided by 0.5, which gives me 44. And then I look at these substances, at these compounds, and I notice that CO2 is the one with a molar mass of 44 grams per mole. Okay. For 18, it says Lewis diagrams for nitrate and nitrite are shown below. Choose the statement that correctly describes the relationship between the two ions in terms of bond length and bond energy. Remember, single bonds are the longest and the weakest. Triple bonds are the shortest and the strongest. Okay. So if I look at these, I'm going to really quickly just average the bond lengths, because remember, for resonance, it's not that you have 2 single bonds and a double bond, it's that you have an average of those 3 bonds. So for nitrate, I have 1 double bond, so that's 2 there, and then 1, 2 single bonds, so that's a total of 4 bonds. So 4 divided by those 3 spots where they are would give me 1.33 average length of the bond. For nitrite, I have 1 double bond, so that's 2 bonds there, and I have 1 single bond, that's 3. 3 divided by the 2 bonding spots, 3 divided by 2 is 1.5. So I know that nitrate has a longer length and it is weaker. Or I know that nitrite is shorter and stronger, and so that corresponds with C. In 19, it says, in an experiment, 2 moles of hydrogen and 1 mole of oxygen were completely reacted according to the following equation in a sealed container of constant volume and temperature. If the initial pressure before the reaction is denoted as P1, which of the following expressions gives the final pressure? So I'm given my initial number of moles. Immediately, if I'm told initial of anything, I know I have to use a nice chart. Okay, so I've got 2 moles of H2, 1 mole of O2, and none of H2O. That's what I'm assuming. My change is going to be minus 2x, minus x, and plus 2x. So if you look at this, trying to figure out which one's totally used up, if my x were 1, both my H2 and my O2 would totally run out. So that's what my x is going to be. It's going to be 1. So 0 plus 2 times 1 would give me 2. Now, if you look at this, I started with 3 moles of gas, and I finished with only 2. So that is 2/3 the amount, right? Because it's 2 divided by the original 3. So my pressure would now be 2/3 the value it was before, which gives me the answer of D. In 20, it says a gas sample with a mass of 10 grams occupies 5 liters and exerts a pressure of 2 atmospheres at a temperature of 26 degrees Celsius. Which of the following expressions is equal to the molecular mass of the gas? So I would set this up, okay? Because I'm not at standard temperature and pressure, I've got to use PV equals nRT. And I'm going to plug in all the values that I know. I know I have 2 atmospheres. I know that I have a volume of 5. I don't know my N. That's what I'm solving for. And then I'm going to take 26 degrees Celsius, and I'm going to add 273 to it. So N, if I divide by 0.8 and 299, N is going to be this. Okay? I'm not going to do any math because they didn't do any math. They left everything set up. To find the molar mass, now I'm going to take 10 grams, and I'm going to divide it by my number of moles because the units for molar mass are grams per mole. So 10 divided by my number of moles. Notice, if you look really carefully, you've got 10 over 2 times 5, which is 10, over 0.8 times 299. Remember, if you have a fraction in the denominator, that's going to cause, instead of dividing by the fraction, you can actually multiply by the reciprocal. So I would be multiplying by 0.8 times 299 over 2 times 5. Well, 10 divided by 10, because it's 2 times 5, would give me 1. Now my 0.8 and 299 are on top because I flipped it when I was multiplying, so my answer is A. In 21, it says how many moles of Na2SO4 must be added to 500 milliliters of water to create a solution that has 2 molar concentration of Na+. Okay? So if I start off with 2 molar of Na+, I need to figure out the concentration of Na2SO4. Good news is I can use a mole-to-mole ratio since I'm dealing with molarity here. So 2 molar times, I'm going to put 1 mole on top, 1 mole of Na2SO4, and 2 moles of Na plus on bottom. Now I'm in concentration of Na2SO4, so that would give me 1 molar of Na2SO4. Now I have the concentration of Na2SO4, and I'm being asked about the moles of Na2SO4. Since molar is moles per liter, I can simply take 1 molar and multiply by the number of liters of water, which would be 0.5. So 1 molar times 0.5, the liters, moles over liters, those liters would cancel with the liters from the 0.5 liters, and that would give me moles. So my answer is 0.5 moles. For 22 to 24, I'm going to use this information here. It says all 3 substances are in the liquid phase. Okay? Which substance would have the highest boiling point, meaning which has the strongest intermolecular attraction? Okay? All 3 of these are polar. Notice the difference. Ethanol has 1 hydrogen bond. Acetone has only dipole-dipole attractions because the oxygen is not attached to a hydrogen, but it is still polar. And then ethylene glycol has 2 possible spots for hydrogen bonding. So which one is going to have the highest boiling point? Well, ethylene glycol will, because it has the most hydrogen bonding. In 23, it says which substance would have the highest vapor pressure. So remember, the vapor pressure is simply a measure of how much gas exists over the liquid. So the weaker your intermolecular attraction is, the more gas molecules you're going to have, because the molecules are not as attracted to one another, meaning it's much easier for them to go into the gas state. So, which has the weakest intermolecular attraction? Well, that would be acetone, because it only has dipole-dipole attractions. It doesn't have any hydrogen bonding. Which of the substances would be soluble in water? Well, all 3 of them are going to be, because remember, polar molecules dissolve in polar molecules. All 3 of those are polar. For 25, it gives us 2 different structures for sulfate. Okay? It says, what is the molecular geometry and structure? A, well, you've got 4 bonding domains, no non-bonding domains, so this would be tetrahedral. What is the SO bond order in structure B? So remember, I'm going to count all of my bonds. I've got 2 sets of double bonds, so that's 4 bonds total, plus 2 single bonds, so that's 6. I'm going to do 6 divided by 4, because I have 4 different spots for bonding. So it's going to give me 1.5. So my answer is C. In 27, it says, which of the following statements regarding the structure B is true? Okay, so in B, keep in mind the average bond order is 1.5 versus 1 for the structure A. So if I look at all of these different options, it says the double bonds must be located opposite to each other. due to additional electron repulsions. That's not necessarily true. Double bonds can be next to each other. It's a more polar molecule. No, we don't have more atoms attached to it. It's the exact same thing, except you've got different bonding. The bonds in the molecule are weaker. Actually, they're stronger because their bond order is 1.5 versus just being 1. And then all bonds in the molecule are identical to each other. That is true because this is going to be a case of resonance, and therefore it's going to be an average of all of those bonds, which means the average is going to be 1.5. So D is your correct answer. Which structure is more likely to correspond with the actual Lewis diagram for the sulfate ion? Now, I'm going to go back really quickly. And we're going to look at structure A and B and determine formal charge. Remember, formal charge is the number of valence electrons minus the number of electrons that have been assigned. Okay? So if I look, for example, at structure A, at oxygen, oxygen has 6 valence electrons, so it's going to be 6 minus, I've got 6 non-bonding electrons. Okay, so I've got 3 lone pairs, so that's a total of 6 electrons, plus 1 bond, because remember, bonds count as just 1. Therefore, I have 7 electrons, so it's going to be 6 minus 7, which would give me -1. So all the oxygens would be -1. For sulfur, it's going to be 6 valence electrons minus the 4 bonding pairs. Therefore, it's going to be a +2 formal charge, because -4 plus 2 gives you the overall charge of sulfate, which is -2. So I have quite a bit of formal charge on this molecule. If you look at structure B, the formal charge for the oxygens with the double bonds are going to be, well, you've got 4 electrons that are non-bonding, and you've got 2 bonding, so a total of 6. So 6 valence electrons minus those 6 would give you 0. So the oxygens are both going to have a formal charge of 0. The other 2 electrons will still be -1, so that still exists. But then the sulfur is going to be 6 minus the 6 different bonds, so 6 electrons that are assigned to it, so it's going to be 0. So to answer this question, to go back to it, which structure is more likely to correspond with the actual Lewis structure? B, and it's B because fewer atoms have formal charges. In 29, okay, so if we look at this, what's going to happen is each of these containers has a volume of 1 liter. If you open up the stopcock, then all of those gases can mix together. They're not going to interact with each other, so ignore that fact and don't let that freak you out. The main point is that if you open the stopcock, the total volume will become 3 liters. Okay? So in 29, it says, which gas exerts the greatest pressure? So I need to figure out, because they gave me grams, I need to figure out the number of moles for each of these. So for helium, it's going to be 20 divided by 4, its molar mass, so I have 5 moles of helium. 40 divided by 20, which gives me 2. And then for nitrogen monoxide, it's going to be 30 divided by 30, which gives me 1. So which has the greatest number of moles? Helium does. The more number of moles you have, the greater the pressure is going to be. Therefore, my answer is A for helium. For 30, it says, which gas has the strongest intermolecular forces? Now, I've got to admit, when I did this problem at first, I got it wrong. Because I said, well, obviously helium and neon only have London dispersion forces. Nitrogen monoxide is polar, therefore it has dipole-dipole attractions. My answer is NO. That was easy enough. Here's the problem, and they trick you. You've got to read the directions at the very top of the page. It says the very last sentence, assume ideal behavior. This is a mean question. If we're assuming ideal behavior, we assume that gases are not attracted to each other at all. Therefore, your answer is D. Okay, so they got me there. Okay, so just be careful. I need to do a better job of making sure. If they say I'm at ideal behavior, assuming there's no attraction between the gas molecules, meaning you have no intermolecular forces. But if you're not at ideal behavior, then NO would have been your answer. For 31, it says the stopcocks are opened. If the tubing connecting has negligible volume, meaning the total volume is going to be 3 liters, by what percentage will the pressure exerted by the neon gas decrease? Okay, so I started off, I'm going to use PV equals nRT. I have a volume of 1 liter in the beginning, and I have 1 mole of neon gas. Everything else stays the same. The only thing that changes for this next one is the fact that now I have a volume of 3 liters. So what has changed? Well, I've taken my pressure and it's going to reduce by 1/3 because nothing else has changed. The only thing that's changed is my volume has tripled, which means my pressure, because pressure and volume are inversely related, my pressure is going to do the inverse of whatever my volume does. So it's going to change by 1/3, which is 33%. So let's look at the free response questions. So for number 1, it says a 250 ml Erlenmeyer flask contains a mixture of 2 liquids, diethyl ether and ethylamine. Now, I don't love this question simply because they don't give you the formula. So it might cause some students to freak out thinking, oh my gosh, I have to know this formula. You don't. So I've included those on the side and I asked you guys to also look those up. The flask is attached to a distillation apparatus and heated until the mixture starts to boil. Now, the point of a distillation apparatus is if you have 2 different liquids, distillation allows you to remove one of the liquids to separate them based on differences in boiling points. So the liquid that has a lower boiling point will become a gas before the other liquid will, and you can actually collect that gas and have it condense again in order to have 2 separate liquids now. So that's what distillation is for. Okay. Why is it important to keep the flask at a constant temperature once the mixture starts to boil? Well, once the mixture starts to boil, that means one of the substances is becoming a gas. Okay? So if you allow the temperature of the solution to rise too much, that could cause the second liquid, which has a higher boiling point, to also evaporate or boil off. And so as a result, that would cause both substances to become gases, and you'd end up with having some sort of impurity or contamination. Okay, so you want to make sure you're just staying at the boiling point of the first liquid and not allowing the second liquid to also boil. In BI, it says which liquid is the primary component of the distillate, meaning what's getting boiled off. Justify your answers in terms of intermolecular forces, okay? So if you look at diethyl ether right here, this would be a nonpolar compound with London dispersion forces, while ethylamine has hydrogen bonding. So as a result, ethylamine is going to have the strongest intermolecular force, which means it's going to stay a liquid. And so diethyl ether is the one that's going to be able to become a gas more easily, so it's going to become the distillate because it has such weak intermolecular forces compared to ethylamine. In II, it says the distillate is not a completely pure substance. Why? Well, it isn't a completely pure substance because it's possible for some of the ethylamine to become a gas. In order for a liquid to become a gas, you don't have to be at your boiling point. Liquids naturally will evaporate. So you're going to have a little tiny bit of ethylamine as a gas. Most of it's going to be diethyl ether, but naturally some ethylamine will be in the gaseous form and going between being a gas and a liquid to a gas, even though it isn't boiling yet. So as a result, you're going to have some ethylamine contaminant in there. In C, it says after the distillate is collected, half of it is transferred into a 250 ml beaker, as shown below. If both containers are left uncovered, which liquid, if either, will evaporate first and why? Well, if you look at these 2 containers, they have the same amount of liquid, the same identity of liquid in them, but notice that for the beaker, it has a larger surface area. In order for a liquid to leave the liquid phase and become a gas, it needs to actually have some sort of contact with the surface of the liquid. So since the surface area of the liquid is greater for the beaker than for the flask, there's more opportunities for liquids to actually leave and become a gas. That means that the liquid in the beaker is going to evaporate first. In 2, it says the carbonate ion is formed when carbon dioxide reacts with slightly basic cold water. Draw the Lewis electron dot structure for the carbonate ion. So I drew this, or they drew this. This is an example of resonance, so you need to draw all 3 of them. Then it asks you to draw the electron dot structure for carbon dioxide, which is right there for you. Okay. In B, it says describe the hybridization of carbon in the carbonate ion. Well, I look and I see that I have 3 bonds total. I have 2 single bonds and a double bond, which tells me that my hybridization is going to be sp2. That's all you need to know. For Ci, it says describe the relative lengths of the 3 carbon-oxygen bonds in the carbonate ion. Well, they're all going to be the same length, simply because, remember, resonance is an average of those 2 single bonds and 1 double bond. So they're going to have the same length. In II, it says compare the average length of the carbon-oxygen bonds in the carbonate ion to the average length of the carbon-oxygen bonds in carbon dioxide. Well, since in the carbonate you have a bond order, and if you think about it, because you have a total of 4 bonds in 3 locations, the bond order is going to be 1.33. While for carbon dioxide, your bond order is 2. So that tells me that the average length of the carbon-oxygen bond for carbon dioxide is going to be shorter than that for the carbonate ion. In 3A, it says explain the difference in the properties given in the table above for each of the following pairs. So if you notice, nitrogen versus oxygen as far as bond strength is concerned, nitrogen has a stronger bond strength. And that's because nitrogen has triple bonds holding them together, while oxygen only has double bonds holding them together. So to be able to know that, because they're asking about bonds, make sure that you're drawing the Lewis structure for those molecules. In II, it says the bond length of H2 versus Cl2. So if we look at bond length, for H2 it's 0.75, for Cl2 it's 1.99. Now they both have single bonds, so I can't use difference in bond order as an explanation. But if you think about it, it actually makes sense that hydrogen would have shorter bonds simply because hydrogen is a smaller atom. In III, it says the boiling points of O2 versus Cl2. So O2 has a boiling point of negative 182, while chlorine has a boiling point of negative 34. Remember, when we're talking about boiling point, we're now talking about our intermolecular forces, not our intramolecular forces. Both chlorine and oxygen have London dispersion forces. So the difference in boiling point is going to be a result of a difference in the number of electrons. Specifically, chlorine has more electrons than oxygen does. Therefore, it is more polarizable, meaning it has a stronger intermolecular force. Since it has a stronger intermolecular force, because it's more polarizable, it is going to have a higher boiling point. Use the principles of molecular bonding to explain why hydrogen and oxygen are gases at room temperature while water is a liquid. Well, hydrogen and oxygen are both nonpolar, therefore they have London dispersion forces. Remember, London dispersion forces are the weakest type of intermolecular force. So that's why they are gases at room temperature, because their attraction for each other is very, very, very weak. Water, however, since it's polar and it has hydrogen bonding, its intermolecular forces are going to be stronger, meaning that at room temperature they are able to hold on to one another much better, and therefore they're going to be liquids at room temperature instead of gases. For 4, it says a student has a mixture containing 3 different organic substances. Here it shows you their Lewis structures. In A, it says if the mixture was dabbed onto chromatography paper that was then placed into a non-polar solvent, rank the RF values for each component of the mixture from high to low after the solvent has saturated the paper. Remember, if you have a non-polar solvent, that means that the most non-polar compound is going to travel the farthest, meaning it's going to have the highest RF value. If your solvent were polar, then your most polar substance would travel the farthest and have the highest RF value. So my task here is to figure out which of these guys is the least polar. Notice N-butanol has a hydrogen bond, which is going to make it pretty dang polar. Your ethyl chloride is polar, but it doesn't have hydrogen bonding, while your N-propylamine has hydrogen bonding as well. So that tells me that even though ethyl chloride is polar, since it doesn't have hydrogen bonding, it's going to have the weakest intermolecular force. It's going to be the least polar, and therefore it's going to travel the farthest and have the highest RF value, when it is moving with a nonpolar solvent. Now, it's a little bit more tricky to compare N-butanol and N-propylamine because they both have hydrogen bonding. But since N-butanol has more electrons, it's bigger, it has more electrons, that means its London dispersion forces are going to be stronger because it is more polarizable. Therefore, since it is more polar, it's going to be ethyl chloride that travels the farthest, followed by N-propylamine, followed by N-butanol. So keep in mind, if you have the same intermolecular force, like hydrogen bonding, find something else that differs between the compounds. And specifically in this case is the fact that N-butanol has more electrons, and therefore its London dispersion forces are going to be stronger. In B, it says if the mixture is poured into a chromatography column and then eluted with a very polar substance, which component of the mixture would leave the column first? Well, now we're looking for the most polar molecule, which would be N-butanol. So since N-butanol is the most polar, it's going to leave the column first. Now keep in mind, if you got this wrong in the very beginning and said that N-propylamine is more polar than N-butanol, the rest of your answers wouldn't be wrong. Okay, so you just simply have to base your answers, if you're trying to grade yourself, base it off of your first answer. Now, obviously, it is the wrong answer if you put N-propylamine instead of N-butanol, but if you had gotten A wrong, you're not also going to get B wrong, so don't let that freak you out. In C, it says the mixture is heated until it begins to boil. Which substance would be easiest to separate via distillation and why? Well, since ethyl chloride doesn't have hydrogen bonding, it has the weakest intermolecular force, therefore it's going to have the lowest boiling point, and it's going to be the easiest to separate out. In II, it says after the substance begins to boil, it continues to be heated at the same rate. Compared to the rate at which it was changing prior to boiling, will the temperature increase faster, slower, or stay the same at the same rate? Well, once you start boiling, all of the heat that's being applied, that's going to be used in order to break intermolecular forces. So as a result, since N-butanol and N-propylamine are going to be increasing their velocity since they aren't boiling yet, right? They're going to be moving faster and increasing their temperature. The ethyl chloride, since it's boiling, it does not change temperature. And so as a result, the rate of temperature change, since your ethyl chloride is no longer changing temperature, the rate of temperature change is going to be less because of that, even though your N-butanol and your N-propylamine are increasing temperature. One of them is not, one of the three is not, and therefore the rate is going to be less. In DI, it says after the components of the mixture have been separated, they are returned to room temperature. Of the three substances which would have the highest vapor pressure at room temperature, well, the substance that has the highest vapor pressure is going to be the one with the weakest intermolecular forces. And that, again, is going to be your ethyl chloride. So ethyl chloride will have the highest vapor pressure because it has the weakest intermolecular force. In II, it says if the substances were heated but not boiled, explain what would happen to their vapor pressures. Well, if you heat anything, you're going to be able to have more of those molecules go into the gaseous phase even if they're not boiling. Remember, boiling is simply when you're in equilibrium, when the rate at which your liquid becoming a gas equals your rate of a gas becoming a liquid. You can still evaporate without actually having boiling. And so if you're increasing the temperature, you're going to have more gas molecules simply because it's easier for those liquid molecules to break their intermolecular attractions and become gases. Therefore, your vapor pressure is going to increase as soon as you increase temperature, even if it's still below your boiling point. In 5, it says the graph above shows the changes in pressure with changing temperature of gas samples of helium and argon confined in a closed 2-liter vessel. What is the total pressure of the two gases at 200 Kelvin? So you simply need to use this table and realize the fact that your pressure of helium at 200 Kelvin is 1 atmosphere, while your pressure for argon is 1.5. So your total pressure is going to be 2.5 atmospheres. In B, it says how many moles of helium are contained in the vessel. Well, I have my pressure, I know my temperature, I know my volume, that was given to me, so I can use PV equals nRT in order to solve for my number of moles. Keep in mind, I cannot use the relationship that 1 mole of a gas equals 22.4 liters because I'm not at standard temperature and pressure. If I were, I could have used that instead of using PV equals nRT. So that's B. In C, it says how many molecules are contained. Well, since I figured out 0.12 moles of my helium gas, I can simply multiply that by Avogadro's number and get that into molecules or atoms of helium. In D, it says molecules of which gas will have a greater distribution of velocities. So I've included in this explanation your Maxwell-Boltzmann diagrams. So if you look at the top one, I'm plotting number of atoms on my y-axis and velocity on my x. Notice if I compare xenon, argon, and helium, the lighter your atom is, the greater the distribution will be of velocities, and the higher your average or RMS velocity will be. So notice, remember I had explained this earlier, but I'll continue to explain this. Imagine this is a string. So imagine I have a string going all the way over that arc for helium. Now, as I increase the mass of my atoms, imagine you're pushing the string back to the left, which causes it to get taller. So we've already seen this graph actually, and look at it below. The same thing applies for temperature. So if you're at a really high temperature, you have a greater distribution and a higher average velocity. As you decrease your temperature, imagine it's a string, you're pushing it back, the average velocity is going to be lower, and the distribution of velocities is going to be less. So keep those curves in mind because that helps you to answer a lot of questions that they might ask. Okay, so for D, which would have the greater distribution of velocities, well, in this case, since helium has a lower mass than argon, it's going to have a higher distribution of velocities. In E, it says if the volume of the container were reduced to 1 liter at a constant temperature of 300 Kelvin, what would be the new pressure? So now I'm keeping my volume, I'm keeping my temperature the same, but now I'm changing pressure and volume. So this is going to be a Boyle's law problem. I know my pressure of helium is 1.5 atmospheres. Its initial volume was 2 liters. Now I've changed that suddenly to 1 liter while keeping temperature the same. So I've got to figure out what my new pressure is going to be. So my new pressure will be 3.0 atmospheres. In 6, it says the reaction above took place and 1.45 liters of oxygen gas were collected over water at a temperature of 29 degrees Celsius and a pressure of 755 millimeters of mercury. The vapor pressure of water at 29 degrees Celsius is 30 millimeters of mercury. What is the partial pressure of oxygen gas? Well, again, remember, we did this in our lab. You need to take the total pressure, which is your atmospheric pressure, 755, and you need to subtract from that the partial pressure of water, which is 30. So your partial pressure of oxygen is going to be 725. In B, it says how many moles of oxygen gas were collected. So in this case, how many moles? I'm going to use PV equals nRT. I need to convert the 725 millimeters of mercury into atmospheres. So they show that there. I wouldn't recommend writing it like that. Just convert it. You know that you have a volume of 1.45 liters. That was given to you. You know your R. And you simply had to take your temperature, 29 degrees Celsius, and add 273 to that to get 302. So you should get, for number of moles, 0.056 moles. In C, it says what would be the dry volume of the oxygen gas at a pressure of 760 millimeters of mercury and a temperature of 273. So be careful, because all of a sudden here, they've changed my pressure and my temperature, but I'm now at standard temperature and pressure. So now that I know my moles of oxygen gas, I can figure out the volume by simply multiplying by 22.4. And so what I would get would be 1.25 liters. Next, it asks, what was the mass of KClO3 consumed in the reaction? Well, I know my moles of oxygen, so I'm going to use my mole-to-mole ratio. For every 3 moles of oxygen, I have 2 moles of potassium chlorate. Okay? That gives me 0.037 moles. I don't love their setup. I would use the stoichiometry that we've always used. Okay, so that's moles of KClO3. Then all I have to do to figure out the mass is multiply by the molar mass of KClO3, which is 122 grams per mole, and that will give me my mass of KClO3, which is 4.51. Okay. In 7, it says equal molar quantities of two gases are confined in a closed vessel at constant temperature. Which gas, if either, has a greater partial pressure? Well, if I have equal numbers of moles, that means my partial pressures will be the same since I have the same volume and the same temperature. Okay? Which will have a greater density? Remember, density is mass divided by volume. So even though I have the same number of moles of gas, since oxygen has a larger molar mass, that means I have more mass of O2. So the mass of O2 is larger. I divide both of them by the volume, which are the same, so that means that the density of oxygen is going to be greater. In C, it says which gas, if either, has the greater concentration, all right? Remember, concentration is moles over liters. Well, I have the same number of moles, and I have the same volume, which means my concentration is going to be the same. In D, which gas, if either, has a greater average kinetic energy? Well, since they're at the same temperature, remember, average kinetic energy only depends on temperature. So they're going to have the same kinetic energy. Now, if it said which has a greater average velocity, then that would be the water molecule because water has a lower molar mass than oxygen does. In E, it says which gas, if either, will show the greatest deviation. Remember, if I'm deviating from my ideal gas law, what that means is that I have an attraction between gas molecules. Because when we say we have an ideal gas, we're assuming that they're not attracted to each other at all. Well, which of those two would have the stronger attraction between molecules? That would be water, because water has hydrogen bonding. So water is going to deviate the most simply because it has hydrogen bonding, while oxygen only has London dispersion forces. For the last problem, this is exactly the lab that we did, so this should be nice and easy. Okay. In A, it says given that the vapor pressure of water is 19 degrees Celsius, at 19 degrees Celsius is 16.5 millimeters of mercury, determine the partial pressure of butane gas. Well, I know the total pressure at 745. I'm going to subtract from that 16.5, which is the partial pressure of water, and then all I have to do with that is divide by 760 in order to get into atmospheres. Okay? In B, it says calculate the molar mass of butane gas from the experimental data given. So remember, based on your lab, in order to determine molar mass, I need to figure out the moles of gas that are released, and I need to figure out the mass of the gas, and I'm going to divide the mass by the moles. So, in this case, to determine the mass of the gas that was released, you take the mass of the lighter before you release the gas, and you subtract from that the mass of the lighter after you release the gas. That is how much gas was released, so it's 0.136 grams. To determine moles, I'm going to use my ideal gas law, PV equals nRT. I know my pressure in atmospheres. I know my volume because that's how much gas was collected. I'm going to set that equal to N times my R times my T. I get my T from just assuming it's the water temperature plus 273, and I get my moles. Now my molar mass is going to be the mass that I got earlier in this problem divided by the moles that I just got, so the molar mass is going to be 49.6. In C, it says if the formula of butane is C4H10, determine the percent error. So for butane, if I use that formula, the molar mass of butane is actually 58. So I've got to take the actual 58, subtract from that the molar mass that I got, which is 49.6, divide by 58, and multiply by 100. So there was a 14.5% error. Remember, you're going to take the absolute value because you can't get negative error. All right. In D, it's wanting us to consider some of the potential errors that could have occurred. And we need to note if that could have caused the error that we saw, specifically that we got a molar mass that was too low. So in I, it says the lighter was not sufficiently dried before massing it after the gas was released. So if you think about it, if you didn't dry the lighter, then the difference in mass before and the mass after is going to be smaller. Okay? Since the mass is smaller than it should have been, that's going to cause your molar mass, which you get by dividing mass by the number of moles, to be too low as well. So that is consistent with the error that we had, and therefore that could work as an explanation. In II, it says the gas in the lighter was not held underwater long enough to sufficiently cool it to the same temperature of the water and was actually at a higher temperature than the water. So, if you think about it, we use temperature for PV equals nRT. Okay? So if the temperature that we used in our calculation was lower than it should have been, that means that the moles that we got would be too high. Because remember, PV equals nRT. If T is too low, that means N is going to have to compensate and be a little too high. So if N is too high, remember I get molar mass by dividing mass by my moles. So if N is too high, that means that my molar mass is going to be too low. So once again, that is consistent with what was observed. In III, it says not all of the butane gas released was collected in the graduated cylinder. So if some of the butane gas was allowed to escape, there are going to be two issues that arise. And they actually, in this answer, only look at one of them. The issue that they looked at is the fact that you are not going to have the correct volume of gas collected, meaning the value that you're going to put is going to be too small. So since PV equals nRT, that's going to cause the volume to be too small, and therefore the number of moles to be too small. Okay, so moles are too small, and they noted that. That's fine. The other issue is if you allow extra gas to escape, that means that the mass of gas that you're going to have used is actually going to be too high because you're allowing extra gas to be released when that wasn't what was being collected. So since the difference is going to be higher, you're going to assume that the mass of gas used was higher than it should have been. In both cases, a mass that's too high and the number of moles that are too low, that's going to cause the molar mass to be too high. Now, since the molar mass is too high, that is an error, but it's not consistent with what was observed because the molar mass that was found in this lab was too low. So that would not be consistent with the student's errors. So really quickly, just as a review, some of these free response questions were really tricky. Okay? Specifically, the fact that in number 1, they did not give you the formula for your 2 compounds, which I disagree with. Okay? They should have given that to you. Okay? In 4, the fact that you have N-butanol and N-propylalamine, which both have hydrogen bonding, and so you're having to rely on differences in London dispersion forces rather than just being able to eyeball it and identify differences in intermolecular forces. That also makes that tricky. So that's a tricky problem. But number 2 should have been fine. Number 3 should have also been totally fine. In number 5, this really isn't too hard of a problem. Just make sure you keep your head on straight. 6, you should have been able to do fine. 7 just requires some thinking, so go back and look at that conceptually. And then 8 should have been a piece of cake because that's what you did. So some of these free response are harder than other big ideas. Don't let that freak you out. Take this opportunity, rewatch explanations, and if you have questions, come in with them, ask your classmates, send me an email, ask me questions.